operating system for high-end computing and cyber physical systems. So, Dr. Jin, can you please share your slides?
Okay, let me try. Do you see my slide?
I do see them.
Okay, great. Okay, let me start. Hello, everybody. Today, I'd like to discuss about the energy efficiency of MPI intra-node communication based on our recent development. This work has been done with my graduate student, Hyun-Wook Jin. Okay. Let me start with a very short summary of what I talked at MOOC 20. In the last year, I presented 3 issues we were investigating with respect to enhancement of MPI intra-node communication. Those were power efficiency, skew tolerance, and better manageability. That time, I briefly mentioned a basic idea to enhance the power efficiency of MPI intra-node communication and presented blocking point-to-point results for small messages. Since then, we have expanded our idea, and now we can support non-blocking communications and large messages. So today, I'm going to share those results and future directions. In this context, I will describe background and motivation from the next slide. Then I will go over what we have done since MOOC 20. And I will conclude my talk. As we know, in HPC systems, the runtimes dedicate a CPU core to each parallel process to maximize the parallelism between processes. Those parallel programming libraries and parallel applications are optimized on the assumption that a parallel process occupies an entire CPU core without sharing it with other processes. With this assumption, MPI libraries use busy waiting to check the completion of outstanding communications. Using busy waiting is acceptable and can provide low latency because a CPU core runs only a single process. However, the longer the busy waiting time, the higher the energy consumption. As shown in this figure, if the sender somehow gets delayed and the message arrives after a long period of time, the receiver will waste the energy while doing busy waiting. Such long busy waiting period may occur due to ununiformity of network latency between processes, asynchronous semantics in communications, and load imbalance. To observe how long processes perform busy waiting, we measured the average per process busy waiting time of MPI Bcast. We ran Bcast on a 16-node night landing cluster. Since we ran the OSU micro benchmark, which is a very simple workload, the absolute time spent in busy waiting was not that big. However, at least we could observe that the busy waiting time is quite random regardless of the number of processes. And it sometimes reaches few hundred microseconds to a few tens of milliseconds. For example, with 128 processes, the busy waiting time was larger than 200 microseconds. And with 1K processes, the busy waiting time sometimes larger than 16 milliseconds. And we believe that a real application may suffer from a larger busy waiting time. So researchers have addressed this issue by exploiting power-saving modes provided by CPUs. Using DVFS that provides different levels of voltage and frequency for operating CPUs is a famous approach. to enhance the energy efficiency. It is also known as P states, where higher P states provide lower performance and reduce the power consumption. Another approach is to promote core idling that turns off hardware components of idle cores. It is known as C states. C0 is the active state in which the processor is executing instructions at the performance level defined by the P state. So in higher C states, the processing of instructions is paused and the power consumption is reduced. In either approach, to minimize the side effect of using energy saving modes of CPUs, researchers have focused on decision policies that determine when and which energy saving mode to enter at runtime. For example, EAM suggested by the MVAPICH team estimates communication phases based on temporal execution patterns and determines whether it enters interrupt-driven mode or not. Countdown arms a timer when an MPI call is invoked and enters a P state if the communication is not finished yet when the timer is expired. EAR and EAR library suggested by BSC detects iteration regions and application characteristics, and then decides the CPU frequency based on an energy model. Any of these decision policies would gain much insight if the MPI library provides internal information. That's why the approaches described in the previous slide were implemented by modifying the MPI library itself or hooking MPI cores. The MPI library not only has valuable internal information in terms of energy saving, but also has a better idea of when to trigger the decision, apart from decision policy. Thus, it will be interesting to have a framework that invokes the decision algorithm at the right time. In this way, we can also separate mechanism and policy. Before describing our framework for energy efficient MPI, let me briefly explain MPI communication channels. As we know, MPI internally uses inter-node communication channels and intra-node communication channels. The inter-node communication channels provide interfaces for interconnects such as InfiniBand, OmniPath, Ethernet, etc. Since inter-node communication channels are not efficient for intra-node communication, MPI libraries use separate channels such as shared memory and memory mapping, which are optimized for intra-node communication. A shared memory channel moves messages from source to destination through a shared memory region for small messages based on eager protocol. A memory mapping channel directly moves messages from source to destination without intermediate copies by means of kernel level support. Though this channel can reduce the number of intermediate data copies, it has a high memory mapping overhead. Thus, the memory mapping channel is used for large messages based on rendezvous protocol. I explained the MPI communication channels because we believe that it is important to efficiently support these multiple communication channels in our framework. As a first step, we target intra-node communication channels such as shared memory and memory mapping. In addition, since our focus is not a policy, but a mechanism, in our prototype, we use very simple decision policy that enters the core idling mode if the process is in the busy waiting phase. Let me explain our decision policy used in our prototype implementation, though it is very simple. The upper figure shows existing case where the sender gets delayed and the receiver spends some time in the busy waiting phase, wasting energy. In our framework shown in the bottom figure, when the MPI library notices that it is about to enter the busy waiting phase, our framework invokes the decision routine that implements the simple policy of core idling. As a consequence, the process is suspended. After that, once the message is ready for receiving, the framework invokes the decision routine again, which will resume the execution of the process at this time. In this way, we can save the energy in between suspending and resuming points. So it is important to identify the points to trigger the decision policy. Since the policy we are currently using simply suspends and resumes processes, I would say those points as suspending and resuming points. Okay, but more precisely, those are the triggering points of decision policy. Let's take a look at the shared memory channel cases first. In this channel, a sending process is suspended when a shared buffer to which the message is copied is not available. This means that the shared memory region is full. On the other hand, a receiving process is suspended when there is no message received. So shared memory is empty. The suspended sending process is resumed when a shared buffer becomes available, maybe because a receiver has drained its message from the shared memory region. The suspended receiver is resumed when a new message arrives. Of course, these do not cover all cases where the decision policy should be invoked, but I just mentioned a few representative cases. Now let's see the cases for the memory mapping channel 2. As I have mentioned, the memory mapping channel is used for large messages that are transmitted through the rendezvous protocol. Thus, the arrival of control messages of rendezvous protocol decides whether the process should be suspended or resumed. Again, this slide shows some representative cases. And let me explain the leftmost case here. The sending process is suspended when there is no clear to send message. This process is resumed once the CTS message sent by receiver arrives. Other cases are also quite similar in that the process gets suspended if there is no control message expected and resumed if the message arrives. Although I don't mention other cases, there can be many more cases, especially if we consider RDMA-like message transmission provided by the memory mapping channel. We can implement our framework in several ways. First, we can consider assembly instructions, such as monitor wait in Intel CPU and wait for event in ARM CPUs. We can also use system calls such as timers, semaphores, and signals. As the CPU independence is an important requirement to us, we prefer the system calls. However, the timer operates periodically, so it is not valid for fine-grained controls. Semaphores are deadlock prone. That is not good. So we decided to use signals. We believe that signaling is easy to support callback functions for our framework, flexible enough to support the inter-node communication channel, and able to leverage existing decision policies used in DVFS and core idling approaches. A drawback of this signaling is that it is lossy, but we resolved this issue in our design. We implemented our framework by modifying MVAPICH 2, or maybe that was the latest version, I think. Okay, now let me move on to our performance evaluation. First, we measured the latency and energy consumption of point-to-point communication. To analyze the impact of different busy waiting times, we added artificial delays in the OS micro benchmark like this. We measured the energy consumption by using Intel-REPL. This slide shows the measurement results with 8 kilobyte messages, which use the eager protocol. The left graph shows the latency, and the right graph shows the energy consumption. Orange bars represent the performance of MVAPICH 2. Since these are the baseline performance, all of these have 100% value in the graphs. And the gray bars show the results of core idling. The green bar represent a hybrid case that uses busy waiting and core idling. In this hybrid policy, the MPI library does busy waiting for a given number of iterations and then enters the core idling mode. We can see that for large delays, our framework with a core idling based policy can save energy up to 93% without performance penalty. However, for small delays, we can see a significant overhead with our framework, which can be mitigated with a hybrid policy of core idling and busy waiting. We believe that a better decision policy will give better numbers. The next slide shows the measurement results with 8 megabyte messages, which use round-robin protocol. For large delays, we see similar results with those of previous slide. However, even for small delays, our framework saves decent amount of energy with a marginal performance penalty. This might be because the artificial delays we added hinder exchanging of round-robin control messages and increase the latency of existing MPI 2. We also measured the execution time and energy consumption of NASPERA benchmarks. We used NUMA-based node that has 20 cores. And then we didn't add artificial delays in these experiments. Instead, we analyzed how long the cores spend in the deepest idle state by using the CPU power command. Okay, this slide shows the measurement results of NPB with 16 processes. Since the node has 20 cores, this is an undersubscribed case. The left graph shows the execution time and energy consumption results. In this graph, 100% represent again the performance of existing MVAPICH 2. As we can see, our framework could save energy up to 12% with a marginal performance penalty. The right graph shows the average per core usage time of the deepest idle state, which was C6 state. This usage time increased significantly in MG with the core idling, which is the main reason for observing a higher energy saving in MG. This slide shows the measurement results of MPB with 32 processes. So this is an oversubscribed case where some processes share the same CPU core. Thus, busy waiting will be more fatal in terms of both performance and energy consumption. As we expected in these experiments, we see higher performance and energy and lower energy consumption with the core idling for all benchmarks. Now let me conclude my talk. In this talk, we have suggested a framework for better support for energy-aware decisions over multiple MPI communication channels. As a prototype, we implemented a signaling-based framework in MVAPICH 2. And to do this, we identified when the decision policy should be triggered on multiple intra-node communication channels. Performance measurement results show that our framework can effectively reduce energy consumption. For example, we could save the energy consumption of MPB class C up to 12% in an undersubscribed case and 91% in an oversubscribed case, respectively. As ongoing work, we are analyzing performance of various system various system architectures with several applications. Especially, we are planning to run QN, which is an electronic structure simulator developed by KISTI. Dr. Liu had a talk to introduce QN in MOOC 17. We are also interested in integrating our framework to MVAPICH 2 EA. As far as I know, MVAPICH 2 EA does not exploit intra-node communication channels. So we believe that MVAPICH 2 EA can benefit from our results. I already showed these graphs in some of previous slides, but we added MVAPICH 2 EA results of these blue bars in these graphs. We will need to investigate more detailed things with the MVAPICH team, but these results show that our implementation can contribute to enhancement of MVAPICH 2 EA, which with respect to intra-node communication. Since MVAPICH 2 EA is not open source, we couldn't take a look at what's happening inside of it. Okay, this is the last slide. We'd like to thank MSIT, NRF, and KISTI for their support, and we also like to thank to the MVAPICH team. And I hope that all we can meet at the OSU campus in the coming year. Thank you.
Thank you, Dr. Jin, for the excellent talk. I think really interesting. So we'll definitely be interested in exploring your contributions to MVAPICH 2 EA. And I think we can contact you after MUG about that.
Great.
Have you thought about extending this work for GPU-based workloads? And what do you expect?
Yes, we want, and we took a look at very basic things with respect to GPU. And what we have seen is that after a submit a kernel to GPU, CPU waits for the completion of the execution of GPU kernels. That time, we can use the CUDA library uses busy waiting, which consumes a lot of energy. So we tried to change it to use core idling, but we realized that there is another interface provided by CUDA, which can block the process running on the CPU. and wakes up the process once the GPU kernel finishes. So we didn't do that because that feature is already there. But we are interested in, but still we couldn't find a good point we are tackling. We can tackle. So let's see. But currently we don't have concrete items to tackle.
Okay. Yeah, that might be an interesting research direction in the future for you. And so have you tried these solutions with any real application? I saw that in your future work that you have plans to work with Q&D, but are there any, and also in the literature, for example?
You mean other than MPB?
Yes, exactly. NPB is a benchmark, right?
Yeah, actually, we read EAM paper published in SC 15. And in that paper, you people showed the performance with the various applications, and we saw that Graph 500 shows a lot of improvement. So we tried to run Graph 500, but it turned out that Graph 500 is more like a computation intensive one. So we couldn't see much improvement. It was, if I remember correctly, it was less than 100%, sorry, 10%.
Okay.
So we wasn't sure whether Graph 500 is a good application to show our benefit. And we are running several applications. What else? Maybe my students remember exactly what applications he ran, but I don't remember exactly. But
sure, okay.
Regarding Graph 500, that was what we observed.
Okay. And have you thought about how will this work be implemented if the MPI application is multi-threaded? So in multiple threads, there will be multiple threads doing MPI communication. So
yeah, that's a very good point, and we will ended up we will have to take a look at the multi-threaded cases as well, and we investigate whether the signaling is suitable even for the multi-threaded cases, because when after some study, if we need to expand our research for multi-threaded, signaling base should work for that environment. And we saw that signaling also can be work for the thread in that we can send a signal to a specific thread. That didn't work on old version of Linux, I think, but now it works well. So we think we can expand our implementation for the multi-threaded cases if needed. And we think that there would be many different issues for the multi-threaded cases. So we need to go over such issues, I think. Maybe we can discuss more detailed things about this direction also.
Sure, thank you. So my colleague Bharat has a question for you. Bharat, please go ahead.
Yeah, I had a couple of questions actually. So the first thing is this: did any of this require root access? Or do you like, so you had mentioned something about dynamic scaling of processor frequency, right? So do you factor that in as well? For example, so do all your designs involve any form of frequency scaling in the processor, or is it like based on signaling just?
Yeah, I got your point. And the EAM paper also mentioned that the DVFS is not enabled in real large-scale supercomputers. But what we are suggesting is that just a framework that can provide a user-defined decision policy that can use DVFS or core idling. So our implementation is not that dependent on whether we can use DVFS or core idling. So decision policy can decide, and we can, our framework provides the interface and invokes the decision policy at the right time. So if that target system support root access, maybe we can use DVFS, but we don't require that DVFS must be supported.
Okay.
Excellent, thank you. So thank you once again, Dr. Jin, for your talk. And I actually forgot to show your introduction. I will just show that now.
It doesn't matter. It's okay. Fine.
So in the interest of time, we'll move to the next talk now.
Okay, thank you.
Thank you. So